Hi, I'm Yousaf Nabhan. Today we are gonna learn functions and relations. We are gonna start with sets. A set is a collection of distinct elements. You may have a doubt what are distinct elements. Distinct elements are nothing but they can be anything. Like if you consider fruits, apple is distinct from orange, but you can't say an apple is distinct from another apple. I think you got it. What am I distinct? Distinct means different, actually. So, if you look into it, you can see that it is a collection of distinct elements. What do you mean by a collection of distinct elements? Maybe when you're a child or a kid, you might have seen that. Your toys might have put all together in a box. It's a similar way. The things what we put in instead of the toy, it can be anything like fruits, name of the football players, or the different kinds of games, or it can be numbers, or it can be real numbers, or rational numbers, or natural numbers. It can be anything, but it should be distinct elements. It should be a collection of distinct elements. A set is denoted as capital letters such as A, B, C, D. It can go until Z. Even I can even put a subscript over it like A1, A2, A3, A4, or if you want, put a subscript like B1, B2, B3, or C1, C2, C3, whatever it is. The elements in a set are represented as a list of elements separated by comma inside curly brackets. For an example, if you look into here, you can see that A is equal to, in the curly brackets, I have put the names of the outdoor games like football, basketball, hockey. A is a set of outdoor games with three elements. You can see that A is a set where we have three elements in it, like football, basketball, and hockey. It is not limited to three elements. It can be any finite number of elements. It can be four elements, five elements, or six even, or whatever the finite which can be counted. Next, we'll go to relations. A relation is a relation or a mapping of elements from one set to another. Let's consider a set A is equal to 1, 2, 3, and 4. A set A contains 4 elements which are 1, 2, 3, and 4. And a set B which contains 4 elements 5, 6, 7, 8. A relation is nothing but, if you look into here from the left side, it is a set A which contains 4 elements 1, 2, 3, 4. And on the right side you can see that it contains 4 elements. It is 5, 6, 7, 8. I related every it should not be every element should be related. It is up to you. Like for relation, it can be like one is, you can see from this example, 1 is related to 5, 2 is related to 5, 3 is related to 6, 3 so again related to 7, 4 is related to 7. As well as you can see that no element is related to 8. It is also possible. Similarly, I can even avoid 1 is relating to 5. That means in a relation, it's not mandatory that 1 is related to any number on set B. It can be related or cannot be related. It is up to you. A relation is nothing but elements in set A or elements in one set is related to elements in another set. In this example, we can see that elements in set A is related to elements in set B. Next, we will see that we denote a relation from a set A to set B as R from A to B. From the previous example, I will show you that this this relation is related from A to B. A to B. That's why we see that R is from A to B. This is how we denote a relation. The next topic we are going to learn is functions. It is an extension of relation where we restrict the mapping from one set to another. A function is nothing but it's a relation, but we put a lot of restriction on it, how it should be related to set B and how much relation or mapping it should have from set A to B. we'll see in the next page. Functions. A function is a relation where every element in set A has an image in set B. You may have doubt about this word. What is an image? Image is nothing but A1 here is related to 5. So here 5 is an image of 1. Similarly, if you ask about the what is 1 is of the 5, it's a pre-image. 1 is a pre-image of 5. Similarly, what is 5 for 1? It is 5 is an image for 1. Okay, a function is a relation. You can see that it's a normal relation where every element in set A has an image in set B. The restriction, you see that the first restriction is every element in set A should have a relation in set B. It cannot be eliminated, as I said before. In the relation, maybe if I don't want the 4 to be related to any other number, any other element in set B, I can avoid it. But in the function, every element in set A should have a image in set B, as well as if you look in, and no element in set A has more than one image in set B, as well as it is restricted that every element in set A should only have one image in set B. If you look into this example, you can see that it is a set of elements 1, 2, 3, and 4, and set B is a set B has elements 5, 6, 7, 8. You can see that on the left side we can see set A, on the right side we can see set B, and every element in set A is related to only one element in set B. Like 1 is related to 5, 2 is related to 8, 3 is related to 6, and 4 is related to 7. From the last relation you can see that 3 here is related to 6 and 3 here is related to 7. It doesn't restrict it from relating to more than 1. But on a function we restrict it. Every element in set A can only have one image in set B, as well as every element in A should have an image in set B. Next, we do not sorry for the mistake, like it's not, it should be function. We denote a function from set A to set B as f from A to B. You can see from here it's function which is related from A to B. That's why it's a function we represent by f. It is from A to B. We can represent the relation and function on a graph. Actually, you might have seen linear equations and quadratic equations. You are mapping or graphing. Yeah, similar way we can graph relation and function on a graph. As a subset of Cartesian product of two sets, we'll see this later. What is a subset and Cartesian product of two sets? Yeah, subset of a set. A subset of a set is a set with only the elements in its superset. You don't have to worry about what I mean by the supersets. Superset we'll see by an example, so you'll know what is a superset. Let us consider a set A is equal to 1, 2, 3, and 4, and B is equal to 4. You may have noticed that B only have one element 4, which is also present in the set A, and B doesn't have any other element which is other than what is present on A. So B is a subset of A. Vice versa is not possible. If you look into it, you can see that A has elements which is not present in B, like 1, 2, and 3 are not present in B. So A is not a subset of B, while B is a subset of A, because B only have the element 4, as well as it doesn't have any element which is other than the elements in 4. So B is a subset of A, but A is not a subset of B. From the set A and B, as I mentioned just now, B is a subset of A where all the elements in B are the elements in set A, and we denote it as B subset of A. This is notation for subset, and the open mouth should be on the bigger set. and the closed part should be on the side of smaller set. Like if you see, B is a smaller set where A is a bigger set. Similarly, A is not a subset of B. As I mentioned, A is not a subset of B. As well as when it's not a subset, we'll just cross over that notation as I mentioned before. If B is not a subset of A, I will just put a cross over it. Similarly, B is a subset, so I mentioned B is subset of A, but A is not a subset of B. As well as I mentioned what is a superset. For B, A is a superset actually. For A, B is a subset, while for B, A is a superset. I hope you understand what it means. It is just vice versa of subset. Next, Cartesian product of two sets. I have already mentioned that at the end of the functions, we are going to discuss what is a Cartesian product of two sets. The Cartesian product of two sets is a set with all the possible combinations of elements in two sets. Cartesian product of two sets A and B are represented as A cross B. Okay, the Cartesian product is nothing but it is all the possible combination or the pairs we can make out of the two sets. And it is denoted like if you are taking the two sets as A and B, it is represented as A cross B. It is denoted as A cross B. I'll give an illustration to better understanding of the concept. Let us consider two sets. A is equal to 1, 2 and B is equal to 5, 6 and 7. We know I'm taking the A cross B, which is a Cartesian product of A and B. From this we can see that it has all the possible pair or all the possible combinations of elements between A and B. You can see that one is related to 5, one is related to 6, one is related to 7 and 2 is related to 5, 2 is related to 6 and 2 is related to 7. You can see that A cross B is equal to 1 5, 1 6, 1 7, 2 5, 2 6, 2 7. From this you might have got a good understanding of what is Cartesian product of two sets. It's nothing but all the possible combinations of elements in two sets. As well as you have to have a clear idea how this set are represented. Since it's mentioned A cross B, I have related from A to B like 1 5, 1 6 and 1 7. What if it is B cross A? It will be related upside from 5 1, 5 2 and 6 1, 6 2 and 7 1, 7 2. They are both different. A cross B is not equal to B cross A, because when flower bracket is mentioned I can put the elements on the left or right without any order, but here I mentioned is the parentheses. In the parentheses order matters. Like if it's left is different from the right, the two things are different. But on a curly bracket, if I put 1 5 on the last and put 2 7 on the first, they're both same. Relations and functions represented as a subset of the Cartesian product. I have mentioned at the end of the functions that relations and function can be represented as a subset of a Cartesian product. Now we are going to see how it is going to work. Let us consider two sets, A and B. A has elements 1, 2 and B has the element 5, 6 and 7. A cross B. You know what is the Cartesian product between A and B? A cross B has the element 1 5, 1 6, 1 7, 2 5, 2 6, 2 7. If you look into this, you can easily come out with an explanation whether it's a relation or a function. From this we can see that one is related to two elements in set B. Three elements in set B. One is related to 5 and one is related to 6 and one is related to 7, as well as 2 is related to three elements in set B. 2 is related to 5, 2 is related to 6 and 2 is related to 7. From this we can come to a conclusion that A cross B is not a function, it's a relation, but it's a relation. For sure it's a relation because relation doesn't have any restriction how it should be related to the next element. Like if you see that it is related to three elements, the relation doesn't has any restriction, but it's not a function, because you see that a function can only have one element as its image. Here it has three elements as its image, as well as two has a three elements as its image. If you look into the set C, you can see that one is only related to one element, one only has an image 7 in set B, as well as two only has an image 5 in set B. You see that it's a function because every element in set A is related to an element in set B. You see, there is only two elements in set A. The two elements also has image in set B. One has 7 and two has 5. So it's a function, as well as it's only related to it only has one image in set B. If you look into it, you can see that it's a function. Every function is a relation after all. If you look into it, you can know that relation doesn't have any restrictions, but having a restriction doesn't mean it's not a relation. A function can be a relation, but a relation cannot be a function. You can see that why a relation cannot be a function. It's not always a function, but it can be a function. If you look into the set D, you can see that 1 is related to 7 and 2 is related to 7. You may have a doubt why the both element in set A has same image in set B. It's not a restriction of a function. A function only mentions that every element in set A should have an image in set B, as well as every element in set A can only have one image in set B. So as per the restriction for a function, it works. One has an image 7 in set B and 2 has an image 7 in set B. It's not at all a problem if two elements in set A has the same image in set B. So it's a function, also a relation, as I mentioned. Keep it in mind, not it, every relation is a function, but all the functions are not relations. I have already explained how it works. It's a relation but not a function, but it's a function as well as it's a relation. As well as if you look into D, you can see that it's a function but it's also a relation. Next, you may have learned linear equations in your 10th grade. We can express a linear equations as y is equal to mx plus b, where y is coordinate in Cartesian plane, as well as b is a y-intercept, and m is a slope. That is, while we are considering linear equations as a function, we'll consider y as f of x. That means it's a function of f, a function of x. Linear equations is a function from x to y. It is nothing but a function from x to y. If you look into this, it's a set of elements x and it's a set of elements y. By the function here, it has x. For each value of the x, we'll have a value for y. But you should keep in mind that the value of the x is completely distinct. Even if you're graphing, you may have know that it will have the value 0, 1, 2, 3, 4, whatever the elements when you graph, but y should not be always be distinct. It can be sometimes same. For we'll come to an example later. You can consider linear equation as a function. Like I can consider y as a function of x, like f of x is equal to mx plus b, as well as it's a function from x to y, because I will put a value in for here x and I will get an input as y. Similar, every value of the x is related to a value in set b. Example for linear equation as a function. Let us consider a linear equation like y is, f of x is equal to 2x. F of x is nothing but it's just y, as you learned in your 10th grade. Here I consider f of x is equal to 2x. It's 2 is the value of the slope, but I consider b is equal to 0. That's why the plus b doesn't exist here. Here if you look into this function, you can see that 1 is related to 2 because I put the value of x as 1, I will get the f of x as 2. You see, and if I put the value 2 here, I'll get the f of x as 4. If I put the value, an arbitrary value n here, I'll get a f of x of 2n. This is how it works. We can even draw a graph for a function. For every functions we can draw a graph. We'll see it later. Yeah, if you see here a graph of function f of x is equal to 2x, the previous one which I showed here, like 1 is related to 2 is related to 4, if you can see that when I put the take the each value here, it is related to 2. It is when I put x as 2, it is related to 4. It's gone like endlessly. Yeah, here it's a graph of f of x is equal to 2x. When I have the value 1, it is go and related to 2, and if I have the value -1, it is, if I have the value -1, it is related to -2. I hope you understand what I mean by a function and how we can represent a function on a graph, and how I and why I represent a y coordinate as f of x, because it is a function of x. Hope you understand. Next, we'll go to quadratic equations as a function. You might also encounter quadratic equation in your 10th grade. I know it's really hard. We'll consider a linear function. Oh, sorry, it's not a linear function. We'll consider a quadratic function, which is y is equal to ax squared plus bx plus c is equal to f of x. I also consider y as f of x here, as I did in linear equation, linear function. I consider y as f of x because it is a function of x, because ax squared plus bx plus c is equal to f of x, where here a, b and c are constants. As you have already learned, what is a quadratic equation will have constants before the x square and x, and there will be a additional constant c. From this you might have noticed that for every value of the x, we'll have a value of y. That is how x is related to y, set of y. x2 is related to y2, and it goes on like xn is related to yn. We'll see an example for quadratic equations as a function. Let us consider a quadratic equation. Y is equal to f of x is equal to x squared. F of x is equal to x squared. When you see just x squared, you may have a doubt where the x and other constants goes. I just consider b is equal to 0 and c is equal to 0 and just a is equal to 1. From the previous one, if you have noticed, you can see that I just consider b is equal to 0. So what it becomes, 0 times x is equal to 0 and c is equal to 0, it goes. So I consider a as 1. 1 times x squared is just x squared. That's why it's f of x is equal to x squared. It's still a quadratic equation. From this, we'll make a set for x, and we'll make a set for y. From this, if you note, you can see that for every value of x, there is an value for y. That is, like if I put the x as 1, x squared, x squared should be 1. And if I put the value of x as 2, x squared is 4. And if I put the value, an arbitrary value n, the x squared is n squared. So every element in x is related to an element in y, and every element in x only have one image in y. I hope you understand. Similarly, we can even draw a graph for a function, a quadratic function. We'll see it in the next page. Yeah, if you see, you can see that for every value of the x, we have a value of y. Let us consider 1. If you consider 1, you might have seen that 1 has a image 1 and 2 has an image 4, as well as -1 has an image 1, and -2 has an image 4. It goes on until infinity. It is a graph of f of x is equal to x squared. Now we'll come to some of the exercise or the examples which will help you understand what is relation and a function. We'll look into the first one. From this you can see that it is a set of a, b and c, and next is a set of 1, 2, 3 and 4. Two elements in the first set is related, but one of them is b is not related to any element it's not related to, it doesn't have an image on the other set. So it's not a function, but it's a relation. It's not a function because every element in the first set should have an image in the next set. The b doesn't have an image, so it's a relation, but it's not a function. We'll see the next example. A has an image 1 here, b has an image 2, c has an image 2 and 3. From this we can see that every element in first set has an image in the next set, but you can also notice that C has more than one image in next set. As per our condition for the function, it should not have more than one image in the next set. Therefore, it's not a function, but it's a relation. Relation doesn't have any restriction actually. We'll see the next example. A has an image 3 and B has an image 1 and C has an image 3. Every element in the first set has an image. It follows the first condition. Next we'll check every element has only one image in the next set. So A only has 1, B only has 1 and C only has 1. Therefore it's a function. This relation is a function, but it is also a relation. This relation is also a function, but the first two are only relations, they are not functions. We'll see other examples. We'll see the first one. We'll check every element has an image as a first condition for function. Every element 0 has an image, 1 has an image, 2 has an image, 5 has an image, 6 has an image. We'll also check whether any of the element has more than one image on next set. So 0 only has 1, 1 only has 1, and 2 only has 1 image, 5 only has 1 image, as well as 6 only has 1 image. So it's a function, it's not a relation, because it follows all two conditions for a relation to be a function, as well as it's a relation as well. We'll see the next example. Here we can see that there is 5 elements in the first set, like 2, 3, 4, 6 and 9. And every element has an image in the next set. Next set, as well as if you look into like a 2 only has one image, 3 only has one image, 4 only has one image, 6 has two images. So it's not a function, it's a relation. It's just a relation, it's not a function because 6 has two images on the next set. I hope you understand what is the difference between the relation and a function. If you look into the third example, we'll see that 2, 8 and 9. Every element in the first set has an image in the next set. For sure, the first condition follows, and we'll see every element only has one image in the next set. Like there is only one element. If you look into, you can see that 2 only has one image in the next set, and 8 only has one image in the next set, and 9 only has one image in the next set. So it's a function. If you look into the next example, let us look into the next example. There are four elements in the first set, and there are 5 elements in the next set. Like the 0, 1, 4 and 9 are the elements in the first set. We'll see every element in the first set has only one has image in the set B, I mean next set. 0 has image, 1 has image, 4 has image, and as well as 9 has image. As well as we'll see whether they have more than one image in the next set. Like 0 has only one image, 1 has one image, and 4 has one image. But if you see, the 9 has two image in the next set. Like 9 has an image 2 and 9 has an image 8. So it's not a function, it is just a relation. We'll go to next. Yeah, we have more example for us to play around with. We'll see the fifth one. Let's see, the first there are two sets of 5 elements and 4 elements, and every elements in the first set has an image, as well as every elements in the first set only has one image in the next set. So it's a function. In the next one we'll see the 6 has the question 6. There are two sets with 3 elements and 5 elements. Every element in the first set has an image, as well as every element only has one image in the set next set. So it's a function. We'll see the next example. I'm just going fast because I hope you understand. I hope you understand because we've been doing a lot of the examples on the last two previous slides. The seventh one. Every element in the first set has an image in the next set, as well as every element in the first set only has one image in the next set. So it's a function, it's not a relation. It's actually, it's also a relation. I'm not saying it's not a relation. Actually, every function is a relation. We'll go to the next question, like eighth one. We'll see that every element in the first set has an image in the next set, as well as every element only has one image in the next set. So it's a function as well. I hope you understand what's the difference. It's not a difference. How we can identify a function from a relation. We'll go next. Yeah, they are the graphical representation of the functions and relations. We'll see how it works. If you look into the first one, you can see that for every value of x, there is only a point in the y-axis. Like it's a negative for in x-axis, we'll take x is equal to negative 2. If you take x is equal to negative 2, there is only one value of y for it. Like if you see, there is only 0. If I put negative 2 here instead of x, we'll get y is equal to 0. There is no 2 value of y. As well as in whichever the point you take on this line, there is only one value for, one image for x, as well as for every value of the x, there is a value of y. I hope you understand. For this function, for every value of x, we'll have a value of y. So it is a function, it's not a relation. We'll go to the next example. It's getting interesting, right? Yeah. In the next example, we see that on the x-axis, for every point on the x-axis, like whatever the point you take on the x-axis, whatever the point you take on the x-axis, sorry, you will only have one y value. If you look into, you'll only get one y value here. Like if you put like x is equal to 0, you will get 3 minus 7. It is y is equal to negative 4. So when x is equal to 0, the only value of the y is only value of only value of y is negative 7. Actually, sorry for the mistake. So for every value of x, there is only a single value of y. So it's a function. I hope you understand, because in the previous representation, I hope you understand that every value of x, you only have one image on the next set. This is a set of y and this set of x. If you see here, if I put the instead of the x, if I give 6, it gives two values, 4 and 6. It's wrong, so it's not a function because it can only have one image. If you look here, you can see that for every value of x we only have one image, that is only one y value. Here as well, for every value of the x we can see that there is only one y value, there is no more than one y value. All right, if you look into the next example, you can see that for every value of in x-axis there is only one y value, there is no more than one y value, there is only 1 point for every point on x-axis. If you look here as well, you can see that for every point it is actually here, it's not touching the line. If you look into this graph, and you may say that for the value of the 0 you have 2 points, one is here and one is here, but actually this line is not touching, it's just going near to this, so it's also a function. It's just approaching this from both sides, but it's not touching 0 actually, so it's also a function. If you look into here as well, it's just approaching the 0 but it's not touching. If you look straight into that, you can see that it's never touches. So y is equal to log 2x is also a function because for every value of x you can see that they have only one y value. We'll see next. Here we come with, for example, there are some tricky examples. If you look into them, you could understand that. We'll take a x value here at this point. For the first example, you can see that there are two y values, one is touching here, which is going to touch here, as well as it is going to go down and touch here. So there is two y values for a single x. What do you think? It has two images. This x value has two images, one is touching here and goes here, and one is touching here and goes here. There are two values you will get for this value of x, so it's not a function because it has two images, so it's a relation. As well as if you see for the every value in the x-axis, like if you take here, you can't find any line, as well as every element in the x-axis has no relation on the y-axis. It is only for the negative values. So it's absolutely fails two conditions, that every x value should have a image, uh, as well as x value cannot have more than two images. So it's only a relation, it's not a function. If you look into the next example, you can see that you might have if you take a point here on x-axis, you can see there is two images, one is touching here and one is touching here, so it will have two images, one is here and one is here, so it has two images. As well as you can see that on this side for x value there is no image at all. For every x value there should be an image, for it should be a function. We'll go to the third example. Oh, it's a little tricky one. We'll see. Let me take a point here at an x-axis. If from here you can see that there is three y values we have, one is here, one is here, and one is here. So for every x value, for it should be a function, it can only have one image. Here we have three images, so absolutely it fails the first condition, even though it passes the second condition that even though it follows the first condition that every value of the x has an image. If you look into every point you can find an image, but a point on the x-axis has three images, one here, and one here, so it's not a function, it's a relation. We'll go to the fourth one. It's the last one, it's the last part of our today's session. If you look into this, you might have noticed that for every point in the x-axis will only meet at one point here. You see, every point you only meet at one point here, you can't meet more than one point here. As well as for the every value, every point in x, it has an image in y-axis. So it's a function because it follows the first condition. Every value of the x has an image in the y-axis, because whatever the point you take, it has a y-axis, it has an image in y-axis. As well as every point in x only has one image in y-axis, because if you look into any point, you can't find more than one image in y-axis. So it's a function. I hope you understand today's session, and I hope we'll continue next session as per your time. So thank you for here for the lecture.